Hello, my name is Martina Gonzalez-Bertello, and I will be presenting my ET-255 Capstone project for the spring of 2020. So just to give some background information, my client is looking to live off the grid somewhere in North Carolina. They are interested in supplementing their power using either biomass, wind, or a micro hydro system. The client has a 5 kilowatt-hour solar-powered system, which is outputting 6,900 kilowatt-hours annually. Taking some information from my first project, they are using 13,839.84 kilowatt-hours annually, and this is without the solar system's input. So subtracting the amount the solar system gives leaves us to just 6,939.4 kilowatt-hours needed to be generated from this next system. Now, when choosing between these three renewable energy sources, we have to weigh the pros and cons of each one. For microhydro, they are simple and affordable with only a minimal environmental impact, but they have fixed maintenance costs and need specific site characteristics to install. Biomass is reliable, reduces weight, and can produce mass amounts of energy, but it requires a lot of land, creating a large environmental impact. Lastly, we have wind power, which is affordable and has low operating costs, but does have noise and visual pollution, as well as being an intermittent source. For this client, we're going to go with a micro hydro system. This system uses the natural flow of water to produce energy. The reason I chose microhydro against wind and biomass is because it has low to none noise air pollution, unlike wind turbines, and it also has a low environmental impact unlike biomass. It is also efficient, affordable, simple, and lets the client live off-grid. I recommend that the client move to somewhere in Watauga County, North Carolina. This region is sloped with many bodies of water available. It is a mountainous region and has up to 135 streams, which provides a safe haven for a macro hydro system. This beautiful region also has popular towns such as Boone and Blowing Rock, but this county also has space for rural living if the client chooses so. It is also located alongside the Watauga River in Tennessee, which crosses over to west of North Carolina. Listed are all the components necessary to build this system. First, we have the intake where the water is pulled away from the stream and into the system. This goes to the penstock where it develops pressure, gets taken to the powerhouse, which houses the turbine, where kinetic energy gets captured, which then generates this energy, ending the process. The system also can include a tail race and a balance of systems, which includes the controller, a battery bank, which won't be necessary for this case, disconnect, a dump load, and a meter. So in order to succeed, the most principal parts of this system are the head and flow. The head being the elevation difference between the source of the water and the turbine, which is typically measured in feet, and the flow, which is a measure of moving water, typically measured in gallons per minute. So to estimate how much power this system needs to generate, you need to multiply head and flow and divide it by 10. 840 watts was calculated from this, and by calculating this within 60 minutes to 24 hours to 365 days, we get 7,358,400,000 watts, which converts to 7,358.4 kilowatt hours annually. So that is how much the system should provide, with a flow of 14 gallons per minute and a head of 10 feet. So for the penstock design, I recommend it to be made of PVC or plastic because of its simplicity, and for the diameter to be 4 inches, which is the optimal size. This should end up costing around $1,000. I recommend an open-ended pipe with a settling container for the intake because it's easy to clean with access, low maintenance, and affordable. This can range from costing $30 to $400, so I'm shooting for the medium to be safe, which is $185. For the turbine, I decided for a low head reaction turbine because the client system will be low flow and also have a low demand. It's also easy to install and the cost is at $500. So installing this system will cost the client around $2,000. The client could lower that price by self-installing some parts of the system, but it is always best to leave it to the experts if you're unsure. Maintenance will occur annually with an average cost of about $100 depending year to year. So these costs are all relative estimates depending on the size, length, and type of some of these elements. So for penstock, its estimate is to be around $1,000. The intake is $185, which was the medium range. The turbine is $500 due to the selected type of turbine. And the installation is approximately $2,000 with the yearly maintenance of $100. So in total, the client system approximately costs $3,785. While you won't gain any profits or break even in the first year and a few years after that, there are some incentives to consider. So first, there is the NC Green Power, which offers to pay a premium price for hydropower that is certified environmentally responsible or low impact by the Low Impact Hydropower Institute. Secondly, North Carolina offers an interconnection incentive with Duke Energy. This allows you to connect to and supply the grid with power coming from your own system. One thing to point out with this one is that the client did state that they want to live off-grid, so this might not be best for their interest. There was a renewable energy tax credit available offering 35% of an incentive to renewable energy owners, but unfortunately that did expire in 2015. Sadly, with our new presidency, many incentives for renewable energy systems have been cut back, but it is possible for the client to find more incentives for their solar system since that source of renewable energy is much more popular in the US, is much more encouraged, and so it has a better chance. That is the end of my Capstone project presentation. My calculations are also included in this post, along with my sources. Thank you so much.